Hello and thanks for using TickBoom. For this question we're told that we've got alpha, beta and gamma and lambda, mu and nu as 6 complex numbers, and we're told that alpha minus gamma divided by alpha minus beta is equal to lambda minus nu on lambda minus mu. And then we're asked to show that the triangles represented by these numbers are similar. So the question's kind of guiding us towards plotting these complex numbers onto an Argand diagram. And then from there we can connect the dots, get our two triangles, and try and use what we're told to then demonstrate the similarity of the triangles. Now, as a preliminary step, what I might do before I even draw up the Argand diagram is if I take what we're told, so we're told that alpha minus gamma on alpha minus beta is equal to lambda minus nu on lambda minus mu. Now, obviously this is what we're told, but I just want to rearrange this ever so slightly to get it into a format that's going to make it a bit easier to go from what we're given to what we need to show. And all I'm going to do is multiply the top and bottom of each ratio on both sides by -1. So I'm not actually changing the condition, but it's just a way of rewriting it ever so slightly. So what we'll get there is gamma minus alpha on beta minus alpha is equal to mu minus lambda on mu minus lambda. So these two things are equivalent. I just think that this version of it is going to be easier to translate from the diagram we're about to draw. So we're told that alpha, beta and gamma and lambda, mu and nu are complex numbers. Now what I'll do, I'll plot each of these on an Argand diagram, and I'll plot them as A, B, C and L, M, N. So let's just draw up an Argand diagram here. So we'll have our real and our imaginary axes with 0 as the origin. Now, where I actually put these points, it's almost not that important. We're not actually told the specific coordinates. So I'll just go with A, B, C, and then just over to the side maybe L, M, N. And let's form our two triangles. Okay, so that's kind of almost just the preliminary steps we need to do to start getting ready to think about how to tackle this question. So we've taken the information and we've got it into the format we need, and we need to show that these two triangles are similar, making use of what we've been told. Now there's a few ways you can go about demonstrating the similarity of triangles, but what I think will be the most straightforward is the side, angle, side approach. So we'll have side, angle, side, side, angle, side. If we can demonstrate that the ratios of the sides are the same and the two angles are the same, then we'll have similar triangles. So the way we can write that is triangle ABC will be similar to triangle LMN if, and our two conditions will be, so we'll write it AC on AB is equal to LMN LN on LM, and our second condition will be that the angle BAC, so this angle here, is equal to the angle MLN, this angle here. So really this question now just becomes simply trying to tick off point 1 and point 2. If we can show each of these are true, then we'll have demonstrated that the triangles are similar. Now, point 1 is relatively simple to demonstrate, so I'll start with that. I might, we'll turn over, but before I do, basically knowing that each of these points are vectors, we know that the length of these vectors is going to be the difference of the two complex numbers. So, for example, well starting with point 1, the vector AC, the kind of the modulus of AC, the length, is going to be equal to gamma minus alpha, where gamma and alpha are the two complex numbers, and the same with AB. The modulus of AB will be equal to beta minus alpha. You see here we've got gamma minus alpha and beta minus alpha, and that's why I've made the first step to get what we've been told in the form gamma minus alpha and beta minus alpha. It just makes it that little bit more direct, the linkage. So it's also true if we go Ln, the vector Ln will be equal to nu minus lambda, and the vector Lm, modulus of that will be mu minus lambda. So now we can kind of get the ratios we're looking for. So we know we're concerned with AC on AB and Ln on Lm. So we'll go AC on AB is equal to gamma minus alpha on beta minus alpha, and Ln on Lm is equal to nu minus lambda on mu minus lambda. Now, kind of we're told that if gamma minus alpha on beta minus alpha is equal to nu minus lambda on mu minus lambda, like we're told that, or at least I derived that from what we were told. If that is true, then it's very easy to conclude that the absolute value of gamma minus alpha on the absolute value of beta minus alpha would be equal to the absolute value of mu minus lambda on the absolute value of mu minus lambda. It's very easy to make that leap because all we're doing when taking the absolute value is either keeping the value positive, or if it was negative, making it positive. The magnitude is still the same, so the magnitude of these ratios would still be the same. And if that's the case, if these two ratios are true, then it's the case, given this ratio is equal to AC on AB, and this ratio is equal to Ln on Lm, we've demonstrated part 1, which is that the ratios of the sides are equal. So that's part 1 done. Now we need to focus on part 2, which is with these angles. And it's a bit trickier to get from what we're told to demonstrating that these angles are also equal. It is possible, but it just takes a few more steps. Now, what I might do while I'm here on this diagram is just draw some lines that are parallel to the axes, because it can help to think about these triangles that we've got as starting from the origin of this vertex here. So even though the origin of our axis is over here, with these vectors, these complex numbers as vectors, it's still the same to think of A as being the origin of this triangle and L as the origin of this triangle. You can make that simplification, and it will just help us think about things, because where we're going to get to here is thinking about these vectors in the different forms of the way complex numbers are displayed. So what I'll do is I'll just note some angles here. So let's just note this angle here as being theta 1, and this angle here as being theta 2. And we'll say this angle here is theta 3, and this angle here is theta 4. And if that's the case, notice that the angle we care about, angle BAC, is theta 2 minus theta 1, and angle MLN, this angle here, is theta 4 minus theta 3. I've just kind of rewritten it in a different way. But now what we can do is we can start to think about our complex numbers. Oops. We can start to think about them in the modulus argument form. I think that's going to be a helpful thing to do here. So we know that basically all complex numbers, you first learned that they can be in the form x plus iy. That's probably the first way you learned about complex numbers. But then hopefully you learn that you can also think about it in the modulus argument form. So we can say r times cos theta plus I sine theta, where r is the modulus, the kind of length, the magnitude of the line, and theta is the argument, the angle of the line. If you have a magnitude and angle, that's another way to represent the point. And hopefully you also have learned that you can represent it as r e to the I theta. And that's called Euler's form. And that comes from Euler's formula, which is that e to the I theta is equal to cos theta plus I sine theta. And it's this format that I think is going to be helpful for this question. Because we can start with the, let's start with the vector AC. So the vector AC can be written in the form the modulus, which will be the magnitude, which will be gamma minus alpha times e to the I theta 2. Because for this vector, it's theta 2 that marks the angle between the vector and what is essentially parallel to the axis. Now, similarly for the vector AB, we can say that is beta minus alpha e to the I theta 1. And the leap that you need to make, the kind of moment of creativity for this question, is to ask yourself, well, what is AC divided by AB? Because notice that's something that we've already dealt with and know about based on what we're told. And in this format, that's equal to gamma minus alpha on beta minus alpha times e to the I theta 2 minus theta 1. Because essentially dividing by the e to the I theta 1, you can just bring it up and make it a negative, so you get this format. And now what we can do is we can think about this ratio, AC on AB, as a complex number itself in the form r e to the I theta. But now r is this ratio, and the theta, the angle, is theta 2 minus theta 1. So the argument of this complex number, well, what we'll say is AC on AB is complex, and it's got a modulus of gamma minus alpha on beta minus alpha, and an argument of theta 2 minus theta 1. Now from there what we can say is therefore the argument of this complex number, or in other words AC on AB, or gamma minus alpha on beta minus alpha, the argument of that is equal to theta 2 minus theta 1, which is equal to the angle BAC. Because remember the angle BAC is theta 2 minus theta 1, the difference. Now, using very similar logic, you can get the same result for ln on lm. I'll take the time to write it out just so that if you didn't completely follow through, you'll get a second crack at it. So what we can do is we can say that the vector ln this time is equal to mu minus lambda e to the I, in this case ln is theta 4, and then vector lm is equal to mu minus lambda e to the I theta 3. Therefore ln on lm is going to be equal to, and we're just going to do essentially the same thing that we did before, but this time for the other triangle. So it'll be nu minus lambda divided by mu minus lambda e to the I theta 4 minus theta 3. Therefore we can say ln on lm is complex with modulus mu minus lambda on mu minus lambda and argument of theta 4 minus theta 3. Therefore the arg of mu minus lambda on mu minus lambda is equal to theta 4 minus theta 3, which is equal to the angle that we care about, MLN, this angle here. Now that we've kind of got to there, we can start to draw some conclusions, because if gamma minus alpha on beta minus alpha is equal to mu minus lambda on mu minus lambda, if that's true, because remember that's where we started from, if that's true, then the two complex numbers, then we can conclude that the AC on AB complex number and the ln on lm complex number are the same. They're the same complex numbers because their modulus and their arguments are the same. So therefore we can conclude, if they're the same complex numbers, that the argument of gamma minus alpha on beta minus alpha is equal to the argument of mu minus lambda on mu minus lambda. And if that's the case, then the angle BAC is equal to the angle MLN. So that required a bit of a logical leap there, so I'll kind of focus on it again. So we've basically derived two complex numbers and their modulus and their argument, and both the modulus and the argument we've been able to state in this format in terms of this ratio and this ratio for each triangle. Now, because we've been able to get the modulus and the argument into that format, then you can conclude that if these two things are the same, then the modulus and argument are the same. So that's the key logical leap. And from there, if we can prove this step 2, so we proved step 1 earlier, that was quite simple, but now we've proved this step 2 that the angles are the same, and therefore we can do our final conclusion that triangle ABC is similar to triangle LMN according to the side angle side approach. So hopefully you found that helpful and that you were able to follow along. I think kind of reflecting back on this question, it is quite tricky, very easy to get caught up on the kind of Greeks and then you know, the points versus the angles and kind of the way that we were given this equality. It's just the tiniest bit unhelpful, but getting it into this format made it much more direct as we start drawing up our vectors. But ultimately, the key to this question is, first of all, you have to kind of know the definition of a similar triangle and be able to deduce that the side angle side approach was going to be the way to go, given what we were given. But from there, it's really just understanding the magnitude of a vector being the difference between the two complex numbers. That's really all we needed to prove part 1. And then for this second part with the angles, getting to kind of this point where you could get the ratio complex number, the ratio that we've been given into the format of a complex number using Euler's form, that's probably the harder part of this question and the element of creativity required. But hopefully now that you've seen this as a possible approach, that you could apply it to other similar questions if you ever face them. So yeah, hopefully you found that helpful, and tick boom.